All right, hello, my name is Sue Bruning, and I'm the Marketing Director here at Cascade and your host for today's webinar. I'd like to welcome you to Cascade's Drilling Webinar Series, and we'll kick the series off today with our Drilling 101 presentation. I just want to cover a few logistics before we jump into the webinar content. Currently everyone is on mute, and we will take questions and comments at the end of Jacob's presentation. You can either submit your question through the chat box and we'll read through those at the end, or you can click on the hand icon that raises your hand and will allow me to unmute your line so you can ask your question. And with that, I would like to introduce today's presenter, Jacob Gallagher. Jacob comes to us from Denver, Colorado. He has 15 years of experience in the drilling and environmental industry. After receiving his BS in chemical biology from UC Berkeley, Jacob chose the most obvious career path and went to work as a helper on a drill rig, and he's never really looked back since. He worked not only as a helper, but moved up as an operator and a project manager before coming into his current role as business development manager with Cascade. His industry experience spans nearly the entire spectrum of Cascade's current service lines. He has extensive experience with both conventional drilling and well methods, as well as our technical service lines like high-resolution site characterization and in-situ chemical remediation, injection, and emplacement. He has knowledge and familiarity with a wide range of different markets, including the environmental, geotechnical, energy, mining, and water supply. So with that, I'm going to turn it over to Jacob Gallagher to talk a little bit more with us about drilling. Jacob?
Thank you, Sue. I appreciate that. Is my screen displayed properly?
Yes. Yep, we can see it.
Okay. Okay. So I'll go ahead and just get going. My goal is to try to get through this in about 45-50 minutes so that we have some time for questions at the end. So there's a lot to go over, so I'm going to jump right into it. Before we start talking about any specific methods, I want to talk about drilling methods in general. And the way that I like to think about drilling methods is that there's sort of three fundamental characteristics that every method has. If you can answer those three questions, then you understand the drilling method or the basics of it. And the first question we have is, what is the method of penetration? So the most simple drilling that we can do is, me in my backyard digging a hole. And the method of penetration is I put weight on the spade of the shovel, and that's how we cut through the dirt, right? So obviously with drilling, we have more sophisticated methods than that, but the concept's the same. You're just digging a hole. The second question is, how do we remove the cuttings from that hole? So you had dirt there before, now it's a hole. The dirt had to go somewhere. You had to move it out. And so the different ways of doing that that's probably one of the key components of what differentiates various drilling methods. And then finally, we have to keep the hole open for some reason. Probably in my backyard, I want to plant a tree maybe, or for whatever reason, I'm digging that hole. Maybe we're putting in a well or whatever, but we're usually not just doing it for fun. We have a purpose, and in order to achieve that purpose, we need to keep the hole open for some period of time. And the way that we do that is varies across different methods. Now, when I'm in my backyard, I'm just relying on the natural competence of the formation to hold the hole open so that it doesn't slough in and collapse. Whenever we have an 8-inch diameter hole down to 300 feet, for example, and we're well below the water table, we need some other kind of means of keeping that hole open, probably. So these are the three fundamental characteristics of every drilling method. And everything that we go through today, it'll be sort of in this context, looking at these three things, and at the end of it, that's how we'll come to understand how the different methods work and what they do. So we have our method of penetration, how we remove the cuttings. Those are what, and the stabilizing of the borehole. That's what makes up a drilling method. And one thing that is, I'll probably harp on a couple times, and if you don't really get anything out of this seminar, you know, I understand you're multitasking, doing emails or whatever. If you remember one thing, it's that the drilling method is independent of the platform or the rig. And what I mean by that is that there are different rigs are capable of different methods, and different methods sometimes can be deployed on multiple platforms. So when we're selecting a drilling method, we want to think about the geology that we're up against and the project objectives that we're trying to achieve. And then the rig type, the platform, has more to do usually with surface conditions. Maybe you need a limited access, small footprint, or tracks because you're off-road, or et cetera, et cetera. So it's important not to get hung up on the method being tied to the rig. And drillers, we're guilty of this as well. We'll talk about a hollow stem auger rig, and I'll call it an auger rig, but that rig is capable of rotary methods and maybe coring methods and other things. But it's just kind of, we get lazy about our vernacular, and we'll refer to a rig by its method, and that's not technically right. They're totally separate from one another. So with that, we'll go ahead and get started with the first method that I want to talk about, which is direct push. And this is a really simple method, simple and economical, but extremely versatile. So our method of penetration is we're directly pushing casing into the ground. We have, I showed on the last slide, there's usually a percussion hammer, or you may use the static, or you could also use the static weight of a rig to basically shove flush threaded casing into the hole. Now this is illustrated with just a solid tip, but you could also put a core barrel on there. There's a lot of different tools that you can run at the bottom of that. In terms of removing the cuttings, of course, my first drilling method is there are no cuttings coming out of this hole, especially if we have a solid tip the way this is illustrated. In this case, the cuttings it's important to remember they still have to be removed from the hole. They're just not being brought to the surface. They're being displaced into the borehole wall. They're getting pushed out of the way. And that's an important limitation of the direct push method, because if the soil can't be displaced, then you get what's called refusal. And the way that we stabilize the hole is with the flush threaded casing itself that we're pushing in. As I said, it's a very economical method. It's also very versatile. You can screw a lot of different tools onto that lead rod and the drill string and do a number of different things. The limitation is, of course, as I mentioned, you have to be able to displace the soil, or if you're collecting a soil sample, you collect it, but still you've got to be able to push it through. So unconsolidated materials are really the type of geology that this works in. And it has limited depth, because as you get deeper and deeper, or with larger diameter casings, the skin friction on that tooling becomes it's a lot of force to overcome. So I mentioned that you can run a lot of different tools on the lead string, and this is an example. These are examples of those tools. High resolution site characterization, or like direct sensing methods, which there's a number of them. Most of them are deployed by a direct push platform, and I would say probably keep an eye out for announcements about other webinars related to these technologies, because I mean this is a whole nother hour-long presentation at least, just going into these types of technologies. Then direct push is also used for more conventional drilling applications like soil groundwater vapor sampling. The tooling is generally pretty small diameter, so while you can install wells, it's going to be smaller diameter wells, not usually much more than 2-inch in diameter. But then there's also in situ remediation amendment delivery, like chemox and chemical reduction or bioremediation things. And again, like the high resolution site tools, that's a whole webinar in and of itself. So we won't go too deep into it, but those are the the idea of this slide is to illustrate the versatility of the direct push method. Here's some examples of rig platforms, track or truck. Geoprobe is a lot of direct push and geoprobe are often interchangeably used in the industry. Geoprobe's not a method; it's a brand of rig. It's like Kleenex is to facial tissue, right? It's a very, very well-known brand, but the method is actually direct push. So the next method I want to talk about is hollow stem auger, which is another very, very common method in our industry and used quite a bit. So our method of penetration, we have an auger bit that claws through the formation. So it's rotational drive, and the bit cuts through the geology. Now the way that we remove the cuttings is the auger has inclined flights that wrap around the outside. And as the auger spins, the cuttings are mechanically lifted to the surface, like the same way grain is lifted in a grain elevator by the inclined auger flights. And the way that we're stabilizing the boring is, as the name implies, the augers are hollow inside. And so that hollow stem provides us access into the borehole for whatever we're doing. If we're running a split spoon sampler to collect soil samples, or maybe we're installing a well or some kind of instrumentation, that's all done through the inside of the hollow stem. Now it's important to recognize one of the features of hollow stem auger is those flights that are around the outside of the auger significantly add to the diameter of the overall tooling. So, for example, an 8-inch diameter auger, in terms of the borehole, is 8 inches in diameter. You only have 4 inches of inside diameter to do whatever you need to do, like to construct a well or whatever. So the diameter of what you're trying to install in the well, if you're installing instrumentation or a well, the borehole diameter is quite different from other methods that have smooth casing on the outside. The auger flights are change the dynamic. So the depth and diameter that you can achieve with auger is based on torque. Obviously it takes quite a bit of torque to turn those augers and to move that soil. As you get larger diameters or deeper depths, you need more torque to achieve those goals. But that assumes that the geology is augerable, that you're able to claw through the formation with the teeth of that auger bit. If you get refusal because it's bottoming out and you're just, it's still augerable geology, you're just running out of the torque because of the depth or the diameter that you're drilling, you can bring in a bigger rig. If you're getting refusal because you've hit bedrock and the bit is not able to cut through it, bringing out a bigger rig is only going to break the tooling with more authority. So here's some examples of auger rigs. CME is, again, that's a brand, a manufacturer. The model numbers, CME 75, 85, 95, those are increasing levels of torque. Then also we're illustrating here, we have different platforms. We have track mounted versus truck and that sort of thing. But then to harp again on my idea that drilling method is independent of the platform, the geoprobe rigs that we saw under the direct push heading, they are also auger capable. They have an auger head that's in the derrick, and if you need to spin augers, they can. They don't have as much torque as regular auger rig, but they are capable of performing the method. And we do it all the time. We call them direct push rigs, but they are technically capable of other methods. So moving along in the sequence here, I'm going to talk about rotosonic, or sonic drilling as it's usually known, which is a really interesting method. So our method of penetration is rotation and resonance. We have counter-rotating cams in the head that generate a resonance frequency in the drill tooling that's axial, vertically along the drill tooling. And literally the particles of soil liquefy at the bit interface, and the soil can either go inside of the core barrel or inside of the tooling, or are pushed out into the borehole wall. The word picture I always use is, if you imagine you have a bowl of sand and you set a marble on top of that bowl of sand, if you were to shake the bowl, the marble will sink down in the sand, because the particles are moving out of the way of the weight of the marble. It's the same thing, except instead of shaking the bowl of sand, we're shaking the marble here. So that usually works better when I'm in person and I can kind of wave my hands around like I'm doing now, but hopefully everybody was able to capture that concept. So the way that we remove the cuttings, they're removed as a core. So the core barrel is brought back to the surface, the resonance is kicked on again, and that's how we extrude the core. And so our soil sample is also our means of removing the cuttings from the borehole. But I mentioned also there are some cuttings that get pushed out into the formation, but the bulk of it is returned as a continuous core. The way that we stabilize the boring is we actually run a core and case sequence. So, and this is we're animating it here. We run the core barrel down, and then we'll wash over a larger diameter outer casing and set that in place, and then retrieve the core. So we're stabilizing the boring with that outer casing, and then here we're illustrating capturing the core, usually in plastic bags or core trays or something like that. Then we run back down in with the core barrel, run to the next depth. Usually 5 or 10 foot intervals are for core barrels. We can run 20-foot cores, but we don't. 10 feet is usually good enough. Then we run more override casing, and that's how the sequence goes. So it's a core and case sequence. As I mentioned, there's a couple nice features about Sonic. One of the reasons why it's gained a lot of traction. You get continuous core as part of the method. You have a flush threaded casing, as opposed to, like I mentioned, the augers, which have the flights on the outside. That flush threaded casing is actually able to seal off different parts of a formation. So if you have environmentally sensitive sampling that you're trying to do, and you want to be positive that you've isolated maybe one aquifer from another, you can use that override casing as a temporary conductor rather than cementing it in. The head design is a whole nother, again, this is a seminar in and of itself, and I think we actually will have a Sonic 101 coming up later, so I won't go too much into it, but it's a very complicated head design, and when it fails, it's extremely expensive. But the method is able to drill through a lot more than you can get through in terms of auger. It can get through more cemented materials and rock, bedrock, boulders, cobbles, a lot of material that is not able to be augered. Sonic will get through it. Also, it can get quite a bit deeper. So moving on to rotary. Now, rotary as a method, that's a very broad description. There's not one rotary method. There's a whole bunch of rotary methods. But in general, they still have to adhere to our concept of our 3 fundamental questions. So our method of penetration is generally by a rotating bit that's suspended by drill pipe, and the weight of the bit plus the drill pipe grinds the formation as it turns. So the bit's rotating, and a weight is applied to it, and that grinds up the geology that you're cutting through. So that's our method of penetration. The way that we remove the cuttings, our method of penetration is pretty consistent across all the rotary methods. You have a rotating bit. But the means of removing the cutting is really where we start to differentiate the different methods. Now you can either use, generally speaking though, you either use the compressed air or an engineered drilling fluid. In the case of a fluid, the viscosity of the fluid suspends the cuttings, and then the fluid is circulated back up to the surface with the cuttings in suspension. And so that's how we're removing the cuttings with fluid-based rotary methods. With air rotary methods, air obviously doesn't have any viscosity, and so we're using the velocity of the air returning up to the surface. So we'll use compressed air down at the drill pipe, and then when it comes up, as it wants to do because it's air, the velocity of that carries the cuttings and formation water, if you're below the water table, back up to the surface. So, and we'll talk more about that in all the different rotary methods that are out there. But that's how we get the cuttings out. Now, how the borehole is stabilized is also quite a bit different from one method to another. If you're using a fluid, a lot of times you'll be relying on the hydrostatic pressure of that fluid-filled hole to prevent the collapse. But also you may be relying on driving a casing, either a welded or a threaded casing. Or if you're in competent rock, oftentimes the formation stabilizes itself. If it's like in bedrock, as an example. So, but as I said, rotary is a generic term, and so the way I like to think about rotary is there's a family tree, so to speak. At the top, this is the broad concept of rotary. And then we have direct and reverse. And direct and reverse refers to the direction of the flow of the drilling medium, whether it's air or a drilling fluid. And we'll see kind of the difference here. But the direction that the medium goes is what differentiates the two sort of subgroups of rotary. And then within that, you can, as I mentioned, you can use air or you can use mud. And you can use air or you can use mud. But they're all different from one another, and so they're all sort of their own methods. And then even within the air method, there's casing advanced systems. Because you don't have that fluid stabilized in your borehole, there's a couple different ways to advance casing during drilling to satisfy our second characteristic, right? So we'll talk about all these. So let's start talking about them. Direct mud rotary is the first one. So, as I said, we have our method of penetration is a rotating bit, and I'm not really going to focus too much on our first characteristic for all the different rotary methods because they're all pretty much the same. It's rotary. It's not a creative name. It's just rotating bit. But so, as I said before, the method of removing the cuttings is really where it starts to get interesting. So with direct mud, what we're doing is we're drilling with a drilling fluid, and the mud pump pumps clean drilling fluid down the center of the drill pipe, and that fluid exits at the bit interface, and it washes away the cuttings that have been ground up by the rotating bit. And then that fluid is circulated back up to the surface and then processed. So the cuttings are separated from the drilling fluid through some kind of cleaning mechanism. This is illustrating a portable mud pit with a linear motion shaker, and here this is a hydrocone, and this is a pretty active mud management system. This could be as simple, and the reason why it's called a mud pit, even though it looks like a complicated machine, is because one of the simplest way to do this is to just have a hole in the ground, and then you have another pit or a channel or whatever, and so as the the returns come up, they could go into just a static pit, and theoretically with time, the heavier cuttings settle down to the bottom, and the clean fluid at the top sort of spills back into your clean sump, and then it gets pumped back down hole again. Now that inactive system, or that passive, just having a hole in the ground, is not really as effective as cleaning as an active system like what's displayed here. And maintaining the properties of the drilling fluid is incredibly important for maintaining borehole stability, and ultimately it has a big influence on, for example, if you're installing a well, that the efficiency of the well that ultimately gets produced, protecting the aquifer from damage. This is another one that honestly we could do a whole webinar on, of just drilling fluid, talking about mud management and all that sort of thing. But this is the basics of it. And so the way that this borehole is being stabilized is from the hydrostatic pressure of the fluid. Now, the fluid, we refer to it as mud, but it's a pretty highly engineered fluid, and one of the key components of it is it creates a thin film around the borehole wall. It's referred to as a filter cake, that not only keeps the formation water in the formation rather than coming in and collapsing the hole, but it also maintains the fluid, the drilling fluid, inside the hole. So the pressure is what's physically keeping that hole open, but the specifics of the fluid and the filter cake that's formed are very important to the function. As I said, the properties are really important. I could talk for an hour about just drilling mud, and I won't do that today, but that's a whole nother webinar. So we're still in the direct subcategory of rotary, and the other drilling medium that you can use is air. So let's look at compressed air, and it's basically the same. So we're running a rotating bit, and there it's rotating for us, and the velocity of so we have an air compressor off here to the side somewhere, and compressed air is running down the center of the drill pipe. Like the mud, it exits at the bit interface, and then it wants to come back up to the surface because it's air, and it comes back very quickly, and the velocity of that air returning to the surface is what's carrying those cuttings back up. You're typically looking for, just as a kind of to understand the difference of how long it takes those cuttings to come to the surface. With mud rotary, you're looking for probably 100 feet per minute, roughly. There's different ranges that are acceptable probably, but just in orders of magnitude, it's about 100 feet per minute for the flow of that fluid that come from the bit interface back up to the surface. Whereas with air rotary, you're in the thousands of feet per minute. So that's sort of to illustrate the velocity that I'm talking about, which is necessary because you don't have that viscosity to suspend the cuttings. Now, with direct air rotary, we don't really have anything stabilizing this borehole. So there's no engineered process to hold the hole open. It's like me digging a hole in my backyard. I don't really have anything to hold the hole open. So direct air rotary is really, it's best applied in a situation when you're in competent material like a bedrock that's gonna stay open. It's also important to note that there's nothing keeping the formation water out of the borehole. Like I mentioned with mud rotary, we have that filter cake, that film around the borehole wall that keeps the groundwater out. This is an open hole, so say you're drilling in rock and you run into a fracture, you're gonna make water along with the cuttings, and so that's a logistical consideration, especially for anybody that's dealing with environmental an environmental site. If that water is contaminated, it has to be dealt with appropriately, and it can make a lot if it's a productive formation. So as I said, there isn't really with direct air, there isn't an inherent method of stabilizing the hole, but if you want to drill air in unconsolidated materials, you'll need to advance a casing somehow. And the first way that we'll talk about advancing a casing is with air rotary casing hammer, or arch. So we're a rotating bit. We have a tricone bit because it needs to be undersized to the casing that we're going to advance. So the first part of it is air rotary. That's the AR, and that's nothing different from what we just saw. We have air coming down the drill pipe. It removes the cuttings, and the cuttings are brought back up to the surface. But the casing hammer, which is how we're stabilizing the hole, is literally a pile driver in the derrick, and it pounds the casing down, and it's independent of the rotational drive of the drill bit. So you have a drill and case where you'll drill, and that's what we're trying to illustrate here in the back. If you see that white that's kind of fading in, that's the idea of this outer casing being driven by this pile driver. And so you'll drill out with the air rotary for a little bit in front of the casing, and then you'll pound the outer casing down to stabilize the hole. So it's a drill and drive, drill, drive, drill, drive sequence. The casing can be welded together, or we mostly run threaded casing. It's very thick and robust, and it's a special thread in order to take the beating, literally, that it's getting. Typically when it's a welded casing, it's going to end up staying in the ground. To get it back out is a lot more cumbersome of a process because you have to cut the welds, but you can do it. Whereas the threaded casing can be removed with casing jacks a little bit easier, like, for example, for well construction or whatever. So this is an excellent method for cobbles and boulders. You can drill larger diameters. It's a flush threaded casing, just like the Sonic, but it can get larger diameters up to like 16 inches. One thing that's important to recognize about this, it is a tricone bit, and the bit is undersized. It's smaller than the outer casing. And so if you were to run into a giant boulder that's bigger than the casing that you're trying to drive, you would have to stop and switch over to air rotary, direct air rotary, which would be fine if you're in bedrock, but if you're in a big boulder, when you get to the other side of that boulder, you don't have a way to continue casing the hole, which is what the next method is really for. So under-reaming is also a direct air method, and I like to think of, if you call air rotary casing hammer rear wheel drive, under-reaming is front wheel drive, and that's because of where the hammer is. So we have an eccentric bit that actually, it cuts a slightly larger diameter hole than the casing that's being advanced. And that's important. So usually, there's a lot of different mechanisms of how they achieve this. There's different brands, Symmetrix and Odex and whatever, and they all have a little bit different way of doing it. But the key feature is that you're cutting a larger hole than the casing that's being advanced. And then there's velocity of compressed air is how we're removing the cuttings from the surface. But that compressed air is also running a pneumatic hammer or a downhole hammer. And so that's what I mean by the front wheel drive. You have the hammer is down at the bit interface rather than with air rotary casing hammer, the hammer was up in the derrick. So that hammering and drilling effect is kind of pulling the casing down as you drill. And you can get through, because it's cutting a larger diameter hole, you can get through a giant boulder, and then on the other side, if you're in loose stuff that would have collapsed, you continuously case the hole through that competent material. And that's the key feature of it. So again, it's flush threaded outer casing. You can also run pretty large diameters. You can also run large diameters just like with arch. It's a very effective method through getting through challenging unconsolidated materials. So where you have big rocks, you know, Volkswagen-sized boulders and things like that, where but it's also loose formations where borehole collapse is a problem. All right. So now those are the direct methods that I wanted to talk about. The next subcategory of rotary is reverse. And so we'll first start with the fluid-based reverse system. And here we have our linear shaker tables. Again, it's a little bit more because we're usually drilling a bigger hole and we have more material to deal with. But again, we have our rotating bit like we do in all our rotary methods. And this is actually kind of more of a mixture of fluid and air, I guess is maybe a better way to say it. But you have your clean fluid is flooding the annular space of the borehole. So instead of using a mud pump, we just run the mud over to our hole, and it just fills up the hole. It floods it. Then we have an air compressor that has an air line down the center of the drill pipe, and that air is and so whenever the fluid comes in, washes the cuttings away from the bit, and the fluid comes into the drill pipe, where it reaches that where that air line is, now all of a sudden we're airlifting the fluid and the cuttings back up to the surface. So it's kind of more of a combination between of air and mud, but our hole is being stabilized by the fluid. We're not running any kind of casing here or anything. It's the fluid itself is what's holding this hole open. So this is what I mean whenever I say the difference between direct and reverse. This is really exact. It's just like direct. I mean, you have a fluid is carrying the cuttings back up to the surface, but rather than going down the inside of the drill pipe and coming back up the annular space, it goes in the reverse direction. So it floods the annular space and then comes up through the inside of the drill pipe. There's a couple different reasons why you would do it this way. One, by having the cuttings come through the inside, they're not interacting with the borehole wall. So if you're worried, in terms of sample quality, you have more confidence that the geology that you're looking at hasn't picked up a bunch of slough from the borehole wall on the way up. And also, it's you could call it a cleaner method. So that borehole wall with the cutting interaction isn't smearing, etc. But also, you can drill a much larger hole because gravity is doing all the work in terms of the diameter, and then everything's coming up through the same diameter pipe on the inside. So whereas with direct mud, in order to maintain that uphole velocity of 100 feet per minute, as your hole gets bigger, you need much, much bigger pumping capacity because you have more gallons per linear foot of hole. Whereas this is the air capacity that you need is the same, regardless of if this is a 17-inch or a 36-inch hole. So that's usually why you switch to flooded reverse over direct mud, is whenever the borehole diameter gets larger, like in supply well installations and that sort of thing. So another example of a reverse circulation, but an air-based method, is dual tube. So with dual tube, we have, and it's hard to illustrate, but it's actually a dual tube pipe. So you have this outer tube and the inner tube are both rotating. They're not really separate the way PowerPoint has it illustrated. It's hard to show. But anyway, the air is coming down through the annulus between the inner and the outer tube, and then it comes up through the inside. Again, and this is an air-based method, so the velocity is what's returning the cuttings. Now, the only thing really holding it open is just the outer tube of the pipe, or the outer tube of the dual tube pipe. And this is a very common exploration drilling method, like in mineral exploration, And the reason is because it's very depth specific. Like I said, those cuttings are coming up through the inside, so there's no interactions with the outside formation to adulterate what those cuttings are. And they come up so quickly because it's with air, it's thousands of feet per minute. You basically know that what's coming out of the cyclone at any given time it's from the depth that you're at. So it's a slim hole exploratory method. It's usually like a 4.5 or maybe a 6-inch diameter hole, and it's for depth specific sampling. It's a good exploratory method. So that's our family tree. We talked about direct mud, direct air, the casing advance, and the flooded, and the reverse with air. There's another rotary method that really kind of is its own thing, and it spans across the entire family. And I couldn't find a place for it, so I just sort of made this. It has its own slide, and that's a dual rotary, which is a pretty amazing method. What you've got is a rotating bit, and you can drill with fluid or air. It's a very versatile. You may run a little bit of fluid in there, you may not, and you're advancing a casing, but the way that you're advancing it is by rotating, and this is where the term dual rotary comes from. You have a rotating inner string and then a rotating outer string, and so the casing is it's not being pounded by a hammer downhole or up in the derrick. It's being rotated in. But then there's also the independent whatever drilling method. So, and this is why it really is able to span across all the different methods, because here I'm kind of illustrating it. I am illustrating it with the air rotary, right? We have an air rotary drilling on the inside, and then we're running that. We're rotating that outer casing to stabilize our borehole. But we could also run with mud rotary on the inside, or we could run reverse or flooded reverse. So the method really spans across all of the different rotaries. So here's an example of reverse dual rotary, where instead of running direct air, we're running dual tube on the inside, right? And so here we have the air coming down the annulus of the dual tube pipe, and it's coming back up. And so you have that great exploration drilling method to get those depth discrete samples. But then we're also rotating and driving that outer casing. That makes sense. So, and why would we do that? Well, because if you're the same reason why we would go to flooded reverse compared to direct mud rotary, we have much lower. So we can drill larger diameter holes with smaller mud pumps or smaller air compressors whenever you run in the reverse direction. And the dual rotary is the outer casing. You can run a pretty large diameter casing. The rigs we run up to 24 inches in diameter. So in general, this rotary rigs also really illustrate my point from the beginning about how the method is independent of the platform. As long as you have a rotational drive and a swivel to run your drilling medium, whether it's air or fluid, a rig can drill rotary. Auger rigs is one example. A lot of the CME rigs that we saw earlier that were hollow stem, there's a rotary capable rigs if they're just plumbed correctly. There's a couple specifics though. So like air rotary casing hammer, you have to have that casing hammer, the pile driver, in the derrick. So that's a pretty specific method that the rig has to be equipped with specific tools in order to be able to do it. Similar to dual rotary, you need a tremendous amount of torque to be able to rotate that outer casing, especially the larger diameter stuff. And you need to have the ability to independently rotate two tooling strings. So only a dual rotary rig can drill dual rotary, but a dual rotary rig is capable of drilling other rotary methods. Same with an arch rig. So those are the only two kind of specifics. And then, as I said, you can go direct or reverse. That really just has to do with the plumbing in the swivel. And the depth is a function of the rig's pullback. So A lot of times when we refer to rotary rigs, we talk about how much weight they can hold, and that's really the limitation of how deep they can go. You add up the weight of the bit and all the tooling, the drill pipe and the stabilizers, whatever that it has to hang in the derrick, and that's its limitation. So a 50,000-pound rig, is able to hold 50,000 pounds worth of drill pipe plus bits and stabilizers, etc. So, and that's depending on what you're running, that's going to be what the limitation is of your total depth. And so we're getting pretty close to the 45 minutes. The last method that I want to talk about is wireline coring. Wireline coring, you have a core barrel. A rotating core barrel is how we're penetrating through typically rock, although there are unconsolidated wireline methods. So it's coring, so it's like sonic. A lot of the way the cuttings are removed is they're coming back as a core. But there is, a certain amount that is not, it's ground up into dust or whatever, and that has to be washed back up to the surface. Wireline coring is typically a fluid-based drilling method, so you need to run a fluid to wash the. In carpentry, it's referred to as the kerf. It's the little bit of material that had to get cut up. That it's not being recovered as a core, but you're also not able to shove it into the formation like you can with sonic, because typically you're drilling with rocks. Now, during the way that we collect that core, there's an inner tube that is the core goes into the inner tube, and there's a latching mechanism that holds it in place during drilling, and then the wire line comes down, catches that latching mechanism, releases the ears for it to be retrieved back up to the surface. This was revolutionary when it got introduced. It used to be that they would be coring, and say you're down, like for mineral exploration, they'd be down at 1,000-something feet, and they'd core their core barrel, and then they would spend however many hours round tripping all the tooling back up in order to recover the core. And whenever the wireline system was invented, it drastically increased coring productivity for exploration purposes, because you don't have to round trip the tooling every single time you want to recover a core. You only have to do it in order to change the bit interface or whatever. So the drill pipe remains in place during core recovery, so that's technically the way that you're stabilizing the hole. Most of the time this method is being performed in rock. That's pretty competent and would hold itself open on its own. So the stabilization method is less important. Kind of the way sonic, the way we change the resonance frequency is to advance the penetration. RPM is really important in coring, so how quickly that core pipe is rotating, and you change the bit based on harder or softer rocks. You need to change it out. Again, coring can be run on a lot of different platforms. There are coring specific rigs that's pretty much all that they do. I mean, they're just set up for it. And those, you could call them coring rigs. But then, like the auger rigs that we saw a lot earlier, they can run HQ core. Rotary rigs, there's slower RPM coring systems like the 94 millimeter that can be run by rotary rigs. The sonic rigs can run wireline core, so a lot of times will drill sonic down to the bedrock interface, and then switch over to wireline coring and just rock core for a while. We need to run a different head because we need that higher RPM, but sonic rigs can do it too. So that sort of brings it back full circle to my what I said at the beginning. If you don't take anything else from this webinar, just please remember that the rig platform is independent from the drilling method. And a lot of times we'll refer to rigs by the method that they do most often, but a lot of times being able to think outside the box a little bit will help you solve tricky problems. So with that, that was about 50 minutes. Not too bad, Sue. I think we got some time for questions, and I hope everybody enjoyed the presentation. And thank you for your time.
Yes, thanks, Jacob. We will open it up now for questions. As I mentioned in the beginning, you can either type your questions in using the chat function, or if you see the hand icon, you can click on that to raise your hand, and then that allows me to unmute your line to allow you to ask your question. Okay, Jacob, our first question came in. What is the best method for clay?
I don't think there's a single best method to answer that question. I think that the different methods have strengths and weaknesses whenever they run into clay. So as an example, air rotary struggles. If you're in a lot of clay, sometimes it can be really hard because the clay, it's sticky, it balls up into large pieces of material or whatever, and so it can be hard to lift them up, right? But at the same time, when the clays get wet, they can swell, and that's a problem. So you have to be careful if you're drilling with mud rotary. And then also, what kind of depths are you at? It changes the equation. In Central California, there's the Corcoran clay that's down at 700 or 800 feet, depending on where you're at. You're not going to be able to hollow stem auger that deep. But if you're in a clay that's and you're only trying to set a 75-foot well, auger works really well in clay. I mean, it's not fun for the helper who has to clean the augers because it usually is a lot stickier than like sands or silts. But it's really good at getting through it. So there's not really a single answer to that question. I think that air definitely has challenges. Sometimes it can be very difficult for sonic as well because the clay attenuates a lot of that energy. It's like the difference between hitting a rock with a hammer versus hitting a pile of Play-Doh. So sometimes it can give sonic fits, but there's
Jacob, it
not
looks
a single
like
answer.
Yep, looks like a couple follow-ups on that one, specific for soil sampling and 30 to 60 feet in the panhandle.
Oh, I would say hollow stem auger or direct push would probably be fine too.
All right. We have another question coming in from Richard Bird. Richard, I have unmuted your line, so go ahead and ask your question. Richard, are you still with us? Oh, we can't hear you. We'll circle back to that one. And we do have some more questions coming in from the chat box. Is sonic viable for drilling long lengths of bedrock?
It is viable. It depends on what you mean by long. Hundreds of feet of bedrock is going to be really hard on the tooling. You're probably going to go through a lot of core barrels. You're going to wear it out the tooling. You're going to put a lot of stress and strain on the rig. So if by long you mean hundreds of feet, the method is capable of doing it. So to answer, viability, yes, it can. It also depends on the competence of the rock. If you're talking about like siltstone or claystone or stuff that's weathered, yeah, absolutely, works great. If you're talking about pure granite or obsidian or something, again, it depends on what you mean by long. If you're saying 20 or 30 feet, the headache of switching over to another method probably doesn't offset the difficulty of penetrating that formation. But if you're talking about hundreds of feet, I think it's worth considering switching methods.
Okay. Our next question, is sonic the best method for achieving undisturbed sample? Shelby tube for geotech. Do the vibrations and rotation disturb the sample?
It's a good question. So you mentioned at the beginning, Sue, I studied chemistry, and even though it's a quantum physics principle, I firmly believe in the Heisenberg uncertainty principle, which says you can't measure something without changing it. And I don't believe that there is any drilling method that has an undisturbed sample. But with that being said, from a geotechnical perspective, typically Shelby tubes are, you're pushing with like auger or in rotary wash. The sonic, the method of penetration is it liquefies the particles in the immediate vicinity of the bit interface. So it's definitely disturbing the soil as it's going down. Now, if you stop and push a Shelby tube, once you get away from that bit interface, you should have undisturbed sample at some point. The question is it disturbed in the first, 2 or 3 inches, the first foot? I don't really know that answer. I don't know that there's been any studies done on that. We might want to reach out internally, Sue, to see if anybody has a white paper or something that they know about for that specifically. But generally, I would say that an order of magnitude, the amount that's disturbed is on the scale of inches or even fractions of an inch.
Okay.
And so if you're in a situation where the upper material is not able to be penetrated by auger or rotary wash or conventional geotechnical drilling methods, the sonic at least gets you to where you need to be in order to push a sample. And so it's better to have some data than no data. And I think that's what most, sonic is a very common geotechnical method, drilling on dams and levees and things like that, where you have that riprap and boulders and things that you have to drill through first. And I think that's the consensus in the geotechnical community is, it might be a little bit disturbed. It's probably not that disturbed in the grand scheme of things, and at least you're able to collect a sample in places where you otherwise probably wouldn't be able to.
Okay. Richard Bird, GoToWebinar is telling me I'm unable to mute your line because you did not put in your PIN code. So I have just emailed that to you. If you are able to enter your audio PIN, then I can unmute your line. Otherwise, you can type it in for us. And a few more questions, Jacob. Lots of folks are asking about the presentation and will it be available. Yes, everyone who is registered for the webinar will receive a link to download the auto recording as well as the slides. So that should come out to you within the next business day. Another question on Rotosonic. When you override casing, where do the cuttings go? Also, how much water is required?
That is a fantastic question. So when you override the casing, if you say you're running a 4-inch diameter core barrel and then you run a 6-inch diameter outside casing, there's a couple inches there of material that has to go somewhere. That's what the carpenters call the kerf. The short answer is that it gets displaced into the borehole. It gets pushed into the borehole wall. Now, the question had 2 parts, and it was asking about drilling about water. And sometimes if you circulate water whenever you're running that outside casing, that's one of the verbs that we use whenever we talk about advancing that casing. They say they wash over the casing. So a lot of times water will be used in that process. And sometimes those cuttings are actually, you'll get a little bit of return. So whenever a sonic driller's running with water, he'll have a pan at the surface, and sometimes you'll have returns coming back up. So in that case, they're not all getting shoved into the formation. Some of them are coming back as cuttings in the water. The answer of how much water is needed, there is not a single answer to that question. It varies a lot with geology. And it also varies a lot with drillers, what I found in my experience. There's some guys that they use a lot more water than others. And it varies quite a bit. In my experience, the guys with the most experience and the broadest range and the most experience are able to get away with using less water than maybe somebody that hasn't done it as much. Whenever you add water, it helps tremendously relieve friction. It cools off the tooling. It helps wash those cuttings out rather than trying to just shove them mechanically into the borehole. It loosens everything up. So adding water makes sonic drilling easier and faster in almost any formation. And so the guys that are really good don't need to use as much as others. But that's a really subjective, hand-wavy answer to a question that had a pretty precise objective, and I apologize, but that's what it is. It's not a definite thing.
All right. Our next question: how is groundwater overexploitation monitored?
Well, if I understand the question correctly, I think this is about monitoring how much groundwater people are pumping from supply wells, and that's a kind of more of a hydrogeological question than a drilling question. But I mean, in general, the way it's monitored is with piezometers or monitoring wells that are measuring what the water table level is, and if that's stable or dropping. If it's dropping, then the resource is probably being depleted faster than it's being recharged. But I think that was the nature of the question. But
all right. My next question is from an audience from John Doherty, and I will unmute your line, John. Go ahead and ask your question. John, are you with us? Okay, I'm going to go to the next question in the chat box. In Mud Rotary, how is a core sample collected?
It generally is not. So if you need to take a split spoon sample, you can do that. So you have to trip out the tricone bit and the drill pipe, and then run in you can run in a split spoon barrel, and you can drive a discrete soil sample. If you need to collect core, there is, I mentioned at the end, go back to the wireline coring. There's a coring system that's called 94 millimeter wireline, which refers to the diameter, but it's specifically set up for wireline coring in unconsolidated material, and you can run that coring system in essentially a mud hole. You're using a drilling fluid while you're to advance the core system. So if you want a continuous core and you're doing mud rotary, that would probably be what I would refer you to. It's a wireline coring method.
All right. I've got 3 more questions in our chat box. If our audience would like to hang on, I know we are a little bit past our time here. This question is about sonic. When washing casing, the water enters between the 4-inch core barrel and 6-inch casing and returns out of the hole on the outside of the 6-inch casing. For environmental drilling, maybe expand upon the use of additional larger diameter casing to seal the hole. So I don't think that's a question. I think that's a comment.
That's a request to expand on it. Yeah, so you can, it's a good point because the fluid's coming back on the outside, and I mentioned that the flush-threaded casing is able to isolate different aquifers from one another. The best way to do that is by telescoping smaller diameter casings inside a larger diameter. So, for example, if you have aquifer A is shallow, aquifer B is deep, and you want to make sure that those aren't talking to each other during the drilling process, you drill down to whatever the barrier is that's separating A and B, and then you set, say, an 8-inch diameter casing. And then you continue drilling into Aquifer B with the 6-inch override, and that you've telescoped the smaller casing inside of the larger, and that's how you achieve that isolation between the two aquifers, I think is what they were asking me to describe.
Okay. The next question, what types of drilling are most effective under artesian conditions and fine sands?
Good question. Mud rotary is always good at that because you're able to use the hydrostatic pressure of the mud. You need to run a different kind of fluid program, usually heavier mud than you would normally do. And when I say heavier, denser, and maybe use polymers and different things to hold out in the artesian conditions. Sonic is also a fantastic method for going into artesian conditions and dealing with heaving sands. It's able to, because of the flush-threaded casing, you're able to get a pretty good pressure. I mean, anytime you hit heaving sands, if you're drilling with hollow stem auger or you're drilling with whatever, the go-to method of dealing with heaving sands is to, fill your tooling or fill your hole with the fluid to try to hold it down. Because Sonic is a flush-threaded casing, you're able to hold that pressure on it compared to like hollow stem auger, for example, where you have the augers aren't screwed together; they're bolted together and they have open joints, and so that you're not able to hold that head pressure as well. The other nice thing about the Sonic method is that once you get past whatever that zone is that has that heave, you are able to case it off, and so it's not continually giving you problems because you're physically isolating it with steel rather than like with mud rotary. You're still fighting it the whole hole down because of your with your fluid properties.
All right, and our last question for the day, other than fluid density, what considerations go into fluid selection?
I assume for drilling fluid, so the 4 parameters that you monitor during mud rotary drilling are density, viscosity. I mentioned the viscosity is what suspends the cuttings, and then the filter cake that I was talking about is you measure that 2 different ways. One, you measure in the thickness of the filter cake that's created on the borehole wall, and then also the relative impermeability of that filter cake is extremely important. And so the test you do, it's called a filtrate loss test, where you take a sample of the mud and you put it under pressure on a filter paper, and the amount of water that's able to get through in terms of a volume, you measure that and make sure that that's within the spec, and then also afterwards the filter cake that gets formed on the filter paper needs to be a specific thickness, and then also the sand content of the drilling fluid is another thing that you're monitoring. That has a lot more to do with the sand is really hard on the tooling, and it wears out the parts of the pump and so forth. But anytime you have anytime you have native material or material that you don't want in the drilling mud, you're going to start to have problems with those other parameters that I mentioned, like density and the filter cake and stuff like that. So, like I said, I literally have an hour presentation just about mud. I could keep going, but those are the 4 things that you want to look for.
Awesome. Well, I am going to close it off on the questions. Jacob's contact information is still up on the screen, so if you have any further questions or would like to talk to Jacob, we do encourage you to contact him directly. His mobile phone and email are both up there. So with that, I'm going to close today's webinar. Thank you very much for joining us. As I mentioned, all registrants will receive an email with a link to download today's presentation. And please consider joining us for future webinars coming up this month. July 27th is part 2 of our remediation cost avoidance webinar. That one is on 3D imaging best practices. In August, we'll have the next webinar in this series, and that'll be Drilling 201 on sonic methodologies and best practices. And then also in August, we have part 3 of remediation cost avoidance and part 4 coming up in September. So jump on our LinkedIn page, Cascade Environmental LLC. Keep an eye on that for the registration details for those webinars. And that's it. Thank you very much, everybody. Have a great day.